All right. Welcome, everyone. Today, I don't have many announcements except the fact that it's extremely cold out there. So be careful. For some of us, we're engineered genetically not for this weather. We suffer. For the others, okay. So, so I only want to remind you for the next talk, which is Mebane Price. She will be February 26th, same place, same time. She will be talking about machine learning count casualties in Syria. The last depressing article I read is about 12% of the people in Syria have been died since the war, which is equivalent to First World War. So anyway, so she will be talking February 26th about that. So I'll be introducing the speakers, but I think they introduce themselves, so I'll do it pre-introduction before they do. So for students that are looking for jobs in data science, this is an opportunity to see what the data scientist is doing in the real world. And that's why they're here. They will tell us how much fun they're having while they're doing that. The two speakers here is Jeff Yao. Jeff got his undergrad from UCLA in math, and then a PhD from UPenn in economics. He had about 10 years of different gigs in the financial world. He introduced himself as econometrician, though he's a data scientist now. Now he's the VP of data science at the company which is called Silicon Valley Data Science, located in Silicon Valley, I presume, right? The other speaker is Harrison. Harrison is actually a Harvard undergrad, then he in physics, and then he did his PhD in physics at Urbana-Champaign, and after that he became a data scientist or data engineer, and he's employee number 12, from what I heard last night. So today they will talk about predicting certain delays at the Caltrain, California train, I presume, and the applications they put together. Jeff, and
thank you. Thanks for having us here. So since we have the introduction, let me skip the introduction slides. So for the talk today, we'll talk about a little bit about our company, who we are and what we do, and our philosophy in conducting business. And then we'll talk about focus. Oh, louder? Oh, it's very loud here for me. So just let me know if I'm not loud enough for the back. So we'll start off with the introductions of our company and the kind of problems that we solve, data science and data engineering problem that we solved. And then we'll pretty much spend about 45 minutes focusing on one of our R&D projects, which is, as you can see, is trying to build a platform and mobile applications to predict the train delay. And along the way, actually, there are many different data science projects within. And so at the end, I actually just want to show you some of the very, very preliminary results that we have in analyzing the data. Again, as I talk, sometimes I have a tendency to decrease my volume. So if, for those of you in the back, you can't hear me, just let me know. Okay, so Silicon Valley Data Science. Okay. So we are a data science and data engineering consulting firm trying to help business to trying to help companies to transform their business using emerging technology and advanced analytics. There are 4 major services that we offer to the clients. They are data architecture, data strategy, and agile data science, and agile data engineering. So we start the company about almost 3 years ago, 2 years and 10 months, and this picture was taken, I think, 5 months ago. So right now we actually have 57 people, even though in this picture we don't have 57 people. 12 of us are data scientists. All of our data scientists are PhDs. And we have 19 data engineers, and some of them actually like Harrison, for example, PhDs who can do both data science and data engineering projects. The rest are data strategists, solution architects, and people in other business units. So our philosophy is that whenever we help clients, we prioritize on helping them to maximize the business value using the emerging technology. So whatever problems we solve, we try to design the solutions with the outcomes in mind. And we do it in an agile way. And throughout the talk, actually, this concept will come up a lot. And so just want to put it out there. And we collaborate with clients very, very closely. So unlike many other consulting firms, so we don't just show up and then disappear for 3 months and then come back again with the solutions. Throughout the entire project, we actually work very, very closely with our clients and the partners. So we have 6 values for SVDS. Our customer comes first, and we seek excellency in what we do. We call the shot, meaning we do what we said. We emphasize a lot on each of the team members because we believe that each one of us is very critical to our team success. We move very fast, so if we want to experiment a lot, we want to fail fast as well if a particular idea doesn't work. We also contribute to the community. By that, what I really means is we have committers to Cassandra or Spark who contribute back to the open source community, and some of us also write research paper and try to publish that as well. In fact, one of our data scientists, he's the author of the Data Science for Business, the textbook, one of the more popular textbook or book. So throughout many of our engagement, we emphasize a lot something what we call the data value chain. So everything from discovery, just from looking at the data, to injecting the data, all the way to analyze, to expose the data, we have this data value or analytic value in mind. I won't go too deep into that right now. And that is because we, I would say 2-3 years ago, we designed this concept called experimental enterprise, which is we want to leverage on open source and emerging technology to set up the environment so that data scientists can experiment on different ideas in a very, very rapid fashion, so that if we succeed and can create value, we want to show that very fast. And if we don't, we know about the result, and then we move on to other ideas. This is particularly important when technology moves very, very fast. In the traditional data architecture development, sometimes you want to plan on things that are like 3-5 years ahead. When technology improves very fast and new ideas come out very, very rapidly, we find that this idea actually turns out to work pretty well. When we work for clients, we deploy very lean team that comprise of data scientists and data engineers. We emphasize a lot the working relationship between the scientists and the engineers in many of the projects that we work on. And these are the two that we normally use. We use Python a lot and other technology. And some of those we actually will show it here in the talk. So here's. So let's dive into some of our case studies.
Yeah, so lest you think that all we do is play with trains, we decided to include a few examples of things we've actually done for clients. The first one is Edmunds.com. Some of you may be familiar with them. They aggregate new and used car sales prices. And they were nice enough and happy with us enough to allow us to use their name in public. So basically their problem was they needed to get manufacturer data from manufacturer documents into their system and categorize all of the different features on various cars so that they could label new cars that were coming into their system, so actual cars that were for sale. Basically, this was all manual. So they would get a PDF from the manufacturer. Some person would have to read through it, figure out what all of the options available on that car were, what the different trims had in terms of optioning, and then put that into a system where they could then categorize actual VIN numbers by the options that they had. So what we ended up doing was we used a third-party machine learning company called Mebane to train a hierarchical model. Edmunds actually had their own ontology, which was hierarchical, so you might have airbags, side airbags, as a subset of that. I believe it went down 3 layers. And basically put glue between the PDF and extracting the data from that and this machine learning model, and then built a nice system for them to be able to kind of validate what was coming out of the machine learning model. And this cut down significantly, as you might imagine, on the amount of time it took to actually label these various options. So here are some numbers. But TLDR, it took them a lot less time to do what took them a long time before. I'll let Jeff talk about the next case study.
One more case study before we talk about the train, because this one is interesting. So this one we are not allowed to name their names, and so the company actually asked us to refer them as the major global brand, MGB. So they engage us to build some new capabilities to help us to transform their business so that, number one, their business is a lot more data-driven and analytic-driven because they do collect a lot of data. And number two, they can actually understand their customer better in order to directly sell to their customers. So as you can imagine, many of the business these days, they do not necessarily sell to you directly. So think of, this has nothing to do with this, I'm just making up an example. So think of Kelloggs cereal. They don't necessarily sell to you directly. They sell to supermarket and then you buy it from supermarket. And so this company is similar in the sense that they do not necessarily sell to you directly, even though they may have a website now that can sell to you directly. And so now that they want to transform the business in order to take advantage of, you can buy stuff from your mobile app, you can buy stuff from your website, they want to make sure that their technology and some of the analytic capabilities can be ready for that kind of transformations. So that's kind of the problem that they have. And so what are their challenges? In many of the companies, this one included, their challenges really is that they have a lot of the legacy system. They have data platform, tools that are usable for the traditional central data warehouse platform. And also their personnel as well are also train and have the skill set that are ready for that platform, but may not necessarily be ready for an open source platform that can take in many different types of data. And so when they are thinking about transforming from the legacy system into what we call to be integrated or deployed system, there were a lot of challenges, and that's one of the reasons why they come to us for help. Another reason is that they have a very, very small data science team, so even though they want to build some models, they don't have enough people to build enough models. And so we actually work very, very closely with them back at the time. We actually work with some of their data scientists directly to actually we share some of the, actually all of the notebooks with them after we build a Jupyter notebook with them after we build the models. And the data science team, another challenge is that the data science team is not working side by side with their IT and data engineering team or platform team. That, in reality, it could create a lot of problems because many times the modeling people do not necessarily know where the data is sitting or where to get the data. Even if you do know them, there are problems with the data that communications create a huge problem. I have a lot of those before I come to VDS. And so our approach to help them is to, well, we deploy agile team. Actually, we deploy many of the small teams to help them at different points in time. Sometimes we work with us and then just communicate with them. Sometimes we actually work side by side with them. And over time, we actually deploy many system and tools and models for them. So this is just a small list of the things that we did for them. So we quantify, for example, they have a mobile app, we quantify the happiness of the app. Like they just want to know, are people happy with our applications? What is the dynamic of the app? Meaning some people can migrate from one version of the app to the other. We did a lot of profiling of their customer base as well, because before you do anything, you actually have to understand your customer. You'd be surprised, many of the companies that may not necessarily understand their customer base. And then it goes on and on. We also did a lot of the text analytics. We actually will talk about sentiment analysis in our train prediction model, and Harrison will talk more about those. One of the last thing is we actually productionize many of their models. So many times when people build models, they are just ad hoc models. They build it, and then you just have a set of code. But if you want to run the model on a very regular fashions, you actually have to put it into a productionized system. So we actually build a platform for them to productionize many of their models. So with that, let me skip over the next two case studies and go right into Caltrain. So some facts about the train. So unlike many of the train systems, this particular train system is a straight line. It connects pretty much between San Francisco, we call the city, and Silicon Valley, as you see over here. So it goes all the way to San Jose and actually Gilroy. I don't take the Caltrain because I live on the other side of the bay, so I come to the office the other way. But Harrison takes Caltrain every day, so he will share with you some of the stories about Caltrain. As you see, the ridership is very high. You know, almost 60,000 people are boarding on a daily basis. And as you can imagine, the economy was going pretty well in the last several years. So the ridership actually increased a lot from, I would say, 2011, 2012 to today. The traffic is horrible in San Francisco. On-time performance is about 92%. Now, it sounds like a high number, but when it is delayed, it is very troublesome. Because for many people, this is the way to go down to Silicon Valley. There are highways that connect between the two, but if you live, let's say, at 7 o'clock in the morning, I don't think you can get to the office by, I don't know, 9 o'clock maybe. So yeah, just 35 miles drive.
On time is defined as within 1 minute of the predicted time, or
the long time?
How do they define on time? What does it mean it being on time? Is it within a minute from the scheduled time, or 5 minutes?
You're talking about delay?
Yes.
Oh, delay, it varies by a lot. How did they get to 92%? That's what they publish. Yeah.
Within 1 or 2 minutes.
Yeah. There are some catastrophic delay, which I will talk about. Caltrains happens to be, let's look at the track again, like this. And their train actually look like, it's on my slide, but not here. By the way, our office is located there. So their train look like this. And you'll be surprised, Caltrain, actually you can walk on the track really easily without going up to a platform. So that's why they have accidents all the time. Hit people or hit car, like on average once a month. So there are 3 types of trains. I'm sharing you with these facts because all of these facts are actually important later on when we are building model or when we are thinking about even how to address the problem. So there are 3 types of trains, local and baby bullet and express. Depends on how many stops they stops along the way. three types of schedule as well: weekdays, weekend, and special. President Day would be holidays. I don't know if Super Bowl has a special schedule. I don't know. Is Baby Bullet stop less or stop more than the Express?
Yeah, so a Baby Bullet is a super express, and an express typically stops at slightly more stops. So a Baby Bullet is really designed to get people from San Francisco to San Jose really fast.
Yeah. And really fast mean like over an hour.
It still takes an hour. It's a very long way.
Yeah. I mean, they run pretty fast, but it's not 20 minutes from San Francisco to Silicon Valley. So there are 92 unit trains per weekday and then 36 on the weekend. So here's the schedule, right? So the schedule over there aligned with the stations here. And the train, so there are unique train numbers. And I want to mention that because actually later on, you see that it defines a lot. Knowing the train numbers, you know what time of the day that it is actually running. And that makes a difference if it is in the rush hour versus not in the rush hour, morning rush hour versus the evening rush hours. So why is it a problem? They actually have real-time departure information on their website. This is something that I actually just cut and paste from their website several days ago. So you actually, if you select the station, you do know when the next 3 trains will be coming. So for example, train number 197 northbound will be coming to the Belmont station in about 129 minutes. You do know. But this app, this API, is not a real-time API in the sense of based on any models. It's just go up with the clock. So that's a problem if a train is delayed. So if you actually look at some of the data, actually Harrison can explain this much better than I can because he experienced this every single day. So the x-axis is the minutes until departure. So let's say now it's 1:24, and the train is supposed to be arrived at 1:34, let's just say 10 minutes, I'm 10 minutes early. And you see that on the y-axis is the expected minutes delay, right? So if you look at the API will tell you, okay, no delay, no delay, no delay. In fact, under 10 minutes here, it will still say no delay. And then it will just go up every now and then, up to a point where it becomes linear. In fact, the train was actually late by, according to this, it's roughly 5 minutes, even though I was there at the departure time. So it's never accurate. A good prediction model should be go up vertical, and then once it get up there, it go horizontal, and then go up vertical, and then go again, right? And so Harrison can tell you, you told me a story about how it goes up minute by minute.
So if there's a really bad accident or even a somewhat more minor accident and your train is delayed, say 10 minutes, you'll be on the platform and it'll say 2 minutes late. Then a minute later, it'll say 3 minutes late. And then a minute later, it'll say 4 minutes late. And as you might imagine, this doesn't tell you a whole lot because you don't know when it's going to stop.
Yeah.
Sometimes it goes up to 25 and you just kind of give up and stop looking at it. But,
so it just have very little information content if you just go to their website and look at this. So that's the API data. Now, like I told you before, every now and then they hit people or hit call. And so when they do hit people or hit call, the API just stops. So in the data, it looks like this. So you will see, again, this is time until schedule, and that's the delay time. You see no delay, no delay, no delay. All of a sudden, oops, something happened on the track, severe delay, and then the entire API goes out, like shut down for every single station. So you get no data because we actually crawl their web and scrape their data. And so you don't see anything until next things you know is already 60 minutes late. So these are the major challenge. So what is the problem? So we want to predict the arrival time for the next K station. So imagine I'm a rider. I come to a particular station, let's say Mountain View, and I want to know, looking at our app, what is the arrival time for the next train or the next 2 trains, right? That is a very basic requirement that we are asking for. We are still working towards that, but at least in this talk, we can show you the data platform that we have built to support these analytics, as well as several analytic projects that we have done along the way to think about this problem. So as I said, one of the major challenges for Caltrain is that the real-time API either doesn't work or it just fails completely, right? The severe system delay, you don't get any information at all. The only thing is Caltrain will have people to go to Twitter and say, oh, okay, we just hit people 10 minutes ago, so expect severe delay. That's the only thing you know. You have to go to Twitter. Note also, this is very important, because for us to build a model, we actually do not have the train location data. We have the schedule. We know what the schedule. We know what exactly for each particular train when they're going to arrive. But we do not know in real life what is the data, where is the location of a particular train. So that creates a lot of problems when we try to build a model. And so our approach is that, well, first is to...
Why can't they just get the location of the train? I mean, there's, or like, how many people are on the train at a given time with GPS actively talking to a train network, right? I mean, shouldn't they in principle be able to pinpoint this thing to a half meter every second?
Surely they could.
Surely they could.
But they don't. I don't know.
No, but couldn't you crowdsource based on the IP addresses of like where everybody is? Couldn't you ping it off of enough stations and somebody has an open GPS?
I think, yeah, that's a great question. And in fact, I'll adjust that. It just.
Does the Caltrain provide the GPS information?
I don't think they have one. I don't think the trains have it.
Yeah, it's part of this is a train that goes to Silicon Valley and doesn't have that
If they have it, they don't tell us.
Yeah. In fact, one of our goals is to make it the prediction model good enough, and then we are actually going to go to talk to Caltrain and ask them to share with us some of their information. Anyhow, so the data sources. So our approach need to build a data architecture platform in order to ingest different kind of data: audio, video, Caltrain API, which you just saw, some social media data, and the GPS data as well. The gentleman who asked about the GPS data. So we actually, that's the idea that we also have as well, is to get the GPS data from individuals. Now, of course, you don't just get a GPS data from anyone, right? You have to rely on the person who download your app so that you can get the anonymous GPS data so that you can use them. And even so, it's not necessarily a trivial problem in order to identify which particular train at a particular location at a particular point in time. So.
Yeah, so I just want to go over briefly what the actual architecture looks like. So this is a rather simplified diagram, but it shows the major components. So we have sensors, audio, video. We have external data, including the API. And then we also have a mobile app, which communicates with the platform via REST API. That's mainly so that we can switch things out in the platform and the app doesn't get confused because there are new tools to deal with. So this is kind of a picture of what a general data platform looks like, just so you know what I'm talking about when I say that. So you have data acquisition, which basically includes any sort of sending data to your system, either internally or externally. So in our case, pulling from Twitter or pulling from our own sensors. Then you have an ingest process, which takes the data, does any sort of analytics on it, and then dumps it into a repository of some sort. And then off of that, off of any repository you can have services like the API that the mobile app communicates via, or analytics, either batch or ad hoc. But to be more specific, this is another fairly simplified, though slightly more specific diagram of the trains architecture. And in a moment, I'll show you the full diagram, and you'll understand why I'm showing you this first instead. Basically, we have a camera and a mic outside of our office, very high tech. We're also pulling from Twitter and the Caltrain API. So all of that goes into Kafka, which, for those not familiar, is just a queue. It's basically a pub subsystem, except it's distributed. So you can put that on a cluster, send messages to it, labeled with various topics, and then anything can subscribe to it and pull those off. So this works well for when you want to save raw data to your platform, but also pull that data off and do analytics on it, and then send the results of that to the platform. And then you can have processes that pull off of it and then publish back to it with new data. That's a fairly common architectural pattern with Kafka. We're also using Spark and Python for streaming analytics. Spark is really good for fast streaming when you have a lot of data coming in. Python works. It's not really made to do that kind of thing, but we made it do that anyway, because at the time we didn't have a Spark cluster stood up. Yeah, so that's the real architecture. I'm not going to spend much time on that because you can't read any of it. But that has all the machines labeled and stuff, so you can see that there are several different components that are all kind of tangled in this spaghetti of communication between them. So in words, I already explained most of this, but Kafka is the message bus. Spark, Python are for streaming analytics. In Hadoop, we store things in either HBase or directly in HDFS, which we can query with Impala. So Impala basically gives you SQL on a distributed system. It's very fast, much faster than a MapReduce job. In terms of the app, we're using a simple Postgres database to save the hard schedule. So the app needs to read, obviously, the hard schedule because that's the primary thing it provides. And that's just stored in a Postgres database. And then we use Spring Boot to set up the REST API that the app then reads all of this information from. So this is just a more detailed diagram of the Twitter architecture. I'm not going to go into too much depth on this because we're going to cover the data science aspect later. But I will point out that this kind of illustrates the use case for Kafka. So the top row is little packets of raw Twitter data on one topic, and then that gets pushed down into an analytics step, which then publishes aggregations of both sentiment and frequency to another topic, and then different things can read off of that topic to figure out if something really bad is happening. So it's a really good way to organize kind of different stages of analysis. And then this is a very simple kind of decision tree for downloading the schedule. Basically, pull it off of Caltrain. Have we seen it before? Yes or no. If not, update the tables, and then the app can read the new schedule off. Okay, so that was the Whirlwind architecture review. So now we're going to talk a little bit about the different types of data science that we did here. Sorry? Yeah. So basically, Jeffrey went over a lot of this. The Caltrain API is less than ideal. We don't have any actual train location data. So the idea is we instrument as much as we can on our side, and then ideally, eventually, we make an app that's useful enough that a bunch of people use it, and then we can just use their GPS data and get train information directly, which is the ideal situation. But it's kind of a cold start problem because you have to get people to share that with you in the first place. So I'll start with audio. This is the first thing that I did when I joined SVDS. And as a new physics graduate, it was, I guess, uniquely suited to the things I actually knew how to do. So where did we get the audio data? At the time, we didn't have any sort of sensors set up. So I ended up memorizing the Caltrain schedule and running outside to the balcony every time one came by and holding up my computer and recording the sound. And then I trained a model off of that. Very high tech in Silicon Valley. Yeah, so this has improved since then. That was about 2 years ago. So nice thing about trains, they use whistles. And whistles are vibrating waves inside a cavity. And so the frequencies that you hear from a whistle are integer multiples of some fundamental frequency. So they have a nice, unique frequency signature, which allows you to distinguish them from, say, a dump truck passing by, or as was the case at our old office, we got a lot of fighter jets flying overhead that were going to Moffett Air Force Base. So just listening to volume isn't good enough, right? Because you might get who knows what, planes, automobiles, but not trains. So we found, or I found by running out to the balcony several times, that the fundamental frequency of a Caltrain whistle is about 340. That's at rest. Obviously, when it's moving, that gets shifted. So we ended up looking for the fundamental plus at least one harmonic of that, so one integer multiple to identify that as a whistle as opposed to something else. So as I just alluded to, you can do better than just identifying that it is a train. You can figure out approximately how fast it's moving, because if the fundamental frequency is shifted very far up or down, that gives you an idea of how quickly it's moving as it goes by. So as Jeffrey mentioned earlier, there are both express and local trains. Local trains stop, and express trains go right on through. Express trains then are moving more quickly, and so their frequencies get shifted. They get higher as they're coming, and then they get lower as they're going away. So the audio model allows us both to say, yes, there's a train, and it's going approximately how fast. So right now, the architecture looks like a microphone hooked up to a Raspberry Pi. The Raspberry Pi has a very lightweight Kafka producer sitting on it, which sends data to Kafka. Kafka dumps out into raw files, and then those raw files are picked up by Python and then disposed of as it finishes analysis. The Python analysis is pretty simple. We check if it's loud. If it's not loud, there's probably not a train there, so we throw it out. If it is loud, we apply a Fourier transform to the audio signal, which is just the discretized version of a normal integral Fourier transform. And then we find the fundamental frequency based on the peaks we see. So if we see more than one frequency peak and they're spaced at the right distance from each other, then we'll call that a train whistle, and then we'll pick the lowest frequency as the fundamental, assuming it's in the right range. And then based on that fundamental frequency, we can figure out whether it's local or express, because we know how fast it's moving. So because I know everybody likes pictures, these are the best pictures I could come up with. It's not this simple usually. They don't look this pretty. I'll see if I can play this. Oops. Nope, that just played on the computer. Well, if you listen very closely, you probably can't hear it. Anyway, that's a whistle, and that is the frequency signature up there. So you can see it has 5 evenly spaced harmonics, and then the spectrogram is also there. It's a spectrogram, so it's frequency versus time. And the other one is just the aggregate of the entire thing. And then we also have a very nice blog post written by one of our data scientists on various things that we tried for classifying local versus express trains. It covers hidden Markov models and other things. So check that out if you are interested in more. Turn it over to Jeffrey.
Okay, thanks. So again, this video processing, image processing, is exactly because we actually do not have their location data. You may think that it's easy to get their data, right? Why don't they just give us the location data and then we can just go ahead and build a model? It really doesn't work that way. And also, we use the R&D projects for us to try many different methodology on different kind of models as well as analytics as well. Because sometimes, we work as a consulting firm for clients, and so we may not necessarily be able to share with you what we do with a particular client. And so R&D is one of the ways that we can showcase some of the techniques that we have tried and platform. Yes?
Sorry, can I ask questions about the previous part?
Yeah. About the previous part?
Yeah, so you say you're classifying different trains, but does that involve more traditional machine learning classification?
Yeah, so right now it's a simple decision tree, mainly because we've condensed the feature space into a maximum frequency that we hear and a minimum. Mm-hmm. So we take a bunch of time steps until the train passes. So we just wait a certain amount of time. And then we take the lowest frequency whistle we heard and the highest frequency, and that tends to be good enough to figure out whether it was local or express. So yeah, it's a simple decision tree, but we've tried other things.
Yeah, and he talks about that. Our colleague talks
yeah,
about
the blog post talks a lot more
about that.
Position?
It's just outside of our office door.
Is that near the track?
Yes, yeah.
Our
yes.
office is literally right next to a track.
I did not mention that, yeah. Both our old and our new office are literally directly behind the train tracks.
And that's how we can actually, in the video one, which I really want to show you, I have a demo as well, to show the audio. I also have, hopefully if we have time, I also have the sentiment analysis that we want to show you as well. Because as you can imagine, the normal delay and the severe delay are very different. So just by hearing the sound, you are not going to identify when it is going to be a severe delay. And so we will actually have to rely on some of our analysis on triggers. Even if you can, these days you can get trigger data about trend extremely easily. But even so, there is still several steps before you can use it to identify normal delay versus a severe delay. So, questions? Maybe one last.
I don't know. Suppose your company is 2 hours away from San Francisco. How do you predict the traffic, the train time from anywhere like San Francisco, 1 hour away from San Francisco? You have no information for that delay.
Yeah,
for that segment at all.
Yeah, that is a good question. So, any forecasting problem, forecast horizon is very important, right? So the question becomes, do I want to predict a train that is 5 hours away that is not even on the track? Or do I just want to predict about the train that is oncoming? So in that case, again, we are still in the process of building the model. So I'm not going to have, or I should say, for any long, in this case it's long, right? 5 hours or 2 hours or 3 hours. For trains that are not on the track, the app can only show you what are the predicted arrival time for that particular station, for that particular train that we have observed in the past. Right? So it's actually very similar to some of the, let's say, traffic, for example. I live actually very far away from the office. I live almost 60 miles away from our office. And so every day I actually have to track the traffic to see how long it takes to get to my house. Fastest is about 60 minutes. But if I want to know, okay, I want to plan to leave at around 7 o'clock tonight. Today is Friday. How much is it going to be? Well, obviously, that traffic predict is not going to tell me how far it's going to be. It can only tell me on a typical Friday, 7 o'clock, it takes about 85 minutes from here to there. So it's very similar when it comes to the train as well. So would it be okay if I move on and I adjust some of the questions later? Otherwise, I won't be able to share with you some of the audio stuff. I do want to show you the audio detection of the train, because this one also has a demo that we run on the notebook. I want to show you the notebook as well. One thing about our research project is that actually many different people participate in different parts. So this is actually done by a colleague of mine. We have a camera actually stick out of our office to record a train passing by. So in general, for audio processing, for moving objects, of course, the notebook that I'm going to show you, it loads the video, it converts into a grayscale, because the images is classified by pixels, right? And then we want to smooth the frames so that we can use it to identify some moving averages, and then we can look at the differences between those in order to do the classifications. So let me switch on to do the demo. So I'm going to show you I'm going to run on this side, the notebook, and then I'm going to show you on that side some of the images. Oops. So again, we load the video first. Oh, it passed by really fast. So let me do it again. It's actually supposed to be slower because I have two windows going on here simultaneously.
Close it first, maybe.
How come it doesn't show? I tried many times this morning. It actually works.
It's because it's a live demo.
Live demos.
Yeah, live demos don't work.
Well-known fact.
So while Jeffrey is troubleshooting that, I will add that
this is already converted to a grayscale. So I actually have the previous picture is that it's actually a color train passing by. This is already converting to a grayscales.
More volume.
Oh.
Nah, I don't think we need more volume.
Oh, sorry.
Did we? Maybe we do. Okay, we did.
Okay.
That'll give you.
Is it better? Is it better in the back? Okay.
Yeah, try that. Yeah.
Hello? Is it better in the back? Okay. Sorry, I hear myself. It's really loud.
It's a little echoey, unfortunately, but
Okay, that's okay.
it does help people in the back.
Okay, I'm so sorry that if you could not hear me. Okay, so after we turn it into grayscale, then we want to smooth out the frames, right? Because we want to identify each frame because it's a moving object. It's not like those. For example, if you go to some tutorial posted by Python, you can see how to classify images, but they're static images. But this one is actually moving. So this is actually smoothing the frame right now. And then after that, again, whenever you talk about moving objects, even for audio as well, you actually have to design a time window for you to calculate some averages so that you can identify when does those change drastically. In fact, the very same technique not only was applied in the audio and video. We actually use that for the trigger analysis as well, because we want to identify when something that is going on and drastically spike. So now it's getting smoother and smoother now, the images. Detect the train. So now it becomes like this, right? Again, all we really care about is that to notice the difference between when a train passes by and when a train doesn't pass by. So we only want to leave the information that are valuable for this detection. We have to classify some threshold. So now it's only that, right? When a train passes by. Okay, now this is the part. So let me move it up a little bit. So when a train passes by, you see this is what we detect on the side. So nothing going on at this point. And then when the train started to pass by, actually those are cars. You start to see the spike up. This is exactly how we use to identify that a train is passing by. And then comes up down as the train goes off. So let me move back. There are more, but let me move back, otherwise I don't have time to talk about sentiment analysis.
Is this robust when you have sunlight or snow, which you never do, I guess?
It rains though, it rains every now and then.
Fall, winter, isn't the robust analysis enough?
Yeah, so that's a good point. At this point, we actually do not have enough sample to detect that. We actually just pick it up. In fact, we hired a new data scientist several months ago. He joined. He actually lived in another location along the track. His balcony oversee the train track as well. So we asked him to put, and his roommate is works for GoPro. So he has a lot of GoPro's camera sitting in his house. And so we asked him to put one of those on his balcony. So right now we actually detect the train from 2 locations. Again, we need more of those so that we can actually see exactly when a train is passing by at a particular point in time. This is nothing more than collecting data still.
Can I make another point?
Yes, please.
Our
Okay.
Mass Transportation Authority, what they do is they have Bluetooth radar detection, and the only thing they do is just trying to pair. And when you're trying to pair, they get the MAC address, and then they do it in another, just trying to pair. Any train with any Bluetooth cell phone will try to pair.
Cool.
And so if you do it, and if you travel around the highways here, now they have these signs, they say 12 miles, 13 minutes. And the way they do it is that just put these Bluetooth detectors, and you don't have to pair. It doesn't pair. Just when anybody goes a car with a Bluetooth, it will try to pair. It will not pair, but the handshake will give them their MAC address, and then they do it later, a mile later, and then they can see the speed of the thing. So if you put one of those, anybody who has a cell phone inside the train, the cell phone will try to pair with the Bluetooth detector. And then you can just do it later, and you see how many.
But we'll put one of those in the train. So we have to talk to Caltrain about it. Yeah. Okay. Sentiment analysis. So we also collect some of the treatise data as well. So I will go pretty fast here because we are close to 2 o'clock. So we actually need to train a model so that it can identify positive and negative sentiments. So we start off, actually quite a while ago, we start off by using a publicly available data set that have tweets on it. And in particular, this particular data set, because you need label in order to train a model, right, to identify sentiment, positive versus negative sentiments. So this particular data set, which is public, and you can download from there, which allows you to get the tweets, and they label the data to be positive and negative using the emojis. And it's a balanced data set the way they construct it. So it's 1.6 million tweets, and then 800,000 positive, 800,000 negatives. So we train it, we use the 80-20 rule. We left out 20% of the data for the training. And so, again, we use some actually fairly basic model to train it, use the count vectorization as well as the bag of words. And for the classification model, we actually use naive Bayes as well as support vector machine. So after we train the model, we evaluate the model on 2 data sets. One is the test data set that we left out from this public data set. And the other one is we actually collect the tweets data that are Caltrain specific. So people talk about the trains. And then we hand label 1,500 of those. So that we evaluate this model on that particular data set to see how it works. And so the result is that the model results on the hand label data set, in general, the support vector machines works better for the naive Bayes model. So then we use this particular data set, use this particular model to evaluate the sentiments on other tweets that we get over time. So So this is an example of the vocabulary that you see from the positive and the negative treats. Now, question becomes, okay, I have treats. How is it going to relate to delay? And is it normal delay or severe delay, right? So we still have to continue to process the data or construct some index so that we can use those index to identify whether or not there is a severe delay versus normal delay. So the question we ask is, we can always pick a particular window and then we can look at the volumes to see whether or not the volumes spike in order for us to do the classifications, positive versus negative. Or we can also look at the volume and then negative sentiment simultaneously to see whether or not there are corresponding to any major delay as well. And lastly, we also need to know if that's not good enough, we also need to know whether or not we actually have to pick out certain keywords to identify severe delay. So let me skip this. So this is an example of the sentiment pattern. So on the vertical axis is the sentiment, and this is average. So the red one is the negative sentiments, and the green one are the positive sentiments. And you see those dots, they represent the volume. So you have to pick a window and see how many of those are over there. And these are the word cloud that we use. So in this particular case, you can see that in general, the positive sentiment is very sparse. Negative sentiment, whenever you're not happy about Caltrain, they're late, then you tweet about it. Now that's a good news because we want to know if people tweet about it, then it's a bad event. Then at least we have a way to identify bad events. So again, the word is a lot late, minute, and things like that. And so you can see that the sentiment is becoming negative. Now, here we are actually at the time when we do the analysis, we try to experiment as to the windows we want to pick in order to identify the volumes, as well as how many tweets as well per window. In this case, 30 tweets per hour. So every one of those will have a dot.
I don't understand how sentiment can be predictive, because isn't it a lagging indicator? Isn't it something that people react?
Sentiment is right now. So again, it's not necessarily predictive in terms of how many minutes you're going to late. So, well, actually, let me jump ahead. I want to identify whether or not a system is going to be severe delay versus normal delay. That's all I want to know, at least using this particular data set. The reason being, if it is a severe delay, it's extremely hard to predict how long it's going to be late. So if I have an app, the only thing I can tell you is it's going to be severe delay. But you will need to have a way to identify it from the data set, let's say if you're looking at the API data. So this is a way, in fact, I will jump ahead and I will just say, we are going to use this to construct something called a calamity index. So that when that index spike, we know that it's going to switch into a severe delay. And so, for example, using econometric terminology, I would, for example, use a regime switching model so that it switches back and forth between a severe delay versus a normal delay. If it is a severe delay, in fact, my model will just tell you, I'm not going to predict anything because first of all, you have very, very few data points and every single severe delay is slightly different. It depends on whether it strike a car or it's so for example, if it's 105 degrees outside, the equipment just doesn't work. And so it causes an hour, 2 hour delay. But if it strike a car, the entire system can be down for like 3 hours, 4 hours because they have to remove the car, something like that. Does it make sense?
I think so. What I'm trying to get my head around is whether or not, I mean, if I'm a passenger on a train and I'm experiencing a delay and I tweet something about my frustration, that's already delayed. I'm not predicting anything.
Yeah, but you're already on a train. You're already on a train. I am trying to see, I'm a rider, I'm waiting for the train, or maybe I'm deciding should I go to take a train or should I not go to take a train. So when I'm looking at the app, it tells me, whoa, okay, it's going to be severe delay. So our app should actually switch to Uber. So go take Uber instead. So it's not of course, for people on the train, it may be useful too. Maybe, okay, you should get off the next station. But I think you're already on the train, you should hear from the operator that, oh, there is a severe delay going on as well.
It's also not only the train that you're on, it's that if yours is stopped, all the other ones behind it are going to stack up. Yeah. And in that sense, it is predictive.
Yeah. Okay, so let me fast forward. So what I'm trying to show you here is that just negative sentiment is actually not enough, because sometimes negative sentiment or high frequency alone is definitely not enough. We know that, right? For example, this one, you see very high frequency on positive sentiment. It has nothing to do with delay. This one is just people talking about Caltrain just announced that they want to increase the capacity for the bike rider and increase the room within the equipment, and then decrease the number of bathroom. Yeah. And negative sentiments sometimes come with false positive as well. And so negative sentiment itself also not enough. And so one of my other colleagues actually go to pick out some of the keywords that reflect severe delay. And then we actually try to classify on these guys. And so we can see that we actually picked several days out of October. It happens that there were 4 very major delays in October that we can identify the event. So you see that the volume spiked a lot, but then at the same time, the volume of the keywords also spiked a lot. In fact, for this particular red one, on October 13, looks like October 14, but it's actually the end of day of October 13, the Caltrain, I think, strike a pedestrian. And so you see the increase in this. And so, which means that we can actually identify very bad event using some of the keywords in the model. Okay. Of course, even before we publish anything on the minutes delay, you can already publish something regarding whether or not it's going to be severe delay. So I was told that it's time's up. So yep, I'm going to stop right now.
How many users of the app are there?
How many right now?
I have no idea.
Several hundreds, I would say. Or thousands. Huh? So over 500? Yeah. Because okay. So we actually have the app. The app right now gives you a static schedule. It doesn't necessarily, because we are still working on a model for the exact time prediction. But having the users getting the app, if you turn it on, we can actually track your GPS location.
And have you thought about users that want the information but don't want the app? So they don't want to contribute to it, but they would want to know with some accuracy about the train arrival time.
What do you mean by contribute?
Well, like the city of Albuquerque tracks their bus system, municipal bus system, and they deliver information about bus arrival times at specific stops with very great accuracy using GPS. They deliver it using SMS. So without having to download an app to your device, it also increases the accessibility because a lot of their population don't have devices that would accommodate a mobile app.
That's reasonable. In our case, if we were actually working for Caltrain, that would be a lot easier of a solution, but it's kind of difficult for a private company to send SMSs to
the general public.
If you have the data, you can distribute it to whoever you choose or whoever buys the information.
We could,
right?
yes.
Okay, one more question. This guy first.
Yeah. Thank you. Thank you.
I would like to ask, generally in your projects, in your approach as data scientist, how important is the dimension of domain expertise? Let's say by trying to solve the problems on the trains, how important is to have somebody that is a consultant on trains or on transportation, or your methods as data scientist is enough, let's say, to address these issues?
So I give my thought, and then Harrison can share his as well. I think domain expertise, certainly, the importance of domain expertise depends on the domain. So in this particular case, it turns out I don't have to be an expert about train engine to be able to predict train delay. But if you are, for example, talking about, let's say I want to price the securities, financial securities, I do think you need to have some domain expertise, even though you may know machine learning and econometrics and statistics. More is always better because the data can only tell you so much, in my opinion. You can use a wide variety of data and techniques, but still sometimes having the domain expertise allow you to explain the results. So yeah, it's useful.
Okay, we need to.
Yeah, thanks.
Thank you very much.
Okay, thank you.